Oh, as far as it comes to Ohms, I hear they can make a lot of noise. Oh, they also happen to, at least at one point, be expressed in a unit known as emus. It's depreciated. Well, our friends down under may disagree. You all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might be just hyper rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. Yes, we are back. And since on, I believe, what was it, Wednesday, we did the Conductance Quantum. Some people were getting excited about it. I know I was. But now we're going to do today the inverse Conductance Quantum. Why? Because we can. It was also the easiest way to do it, because literally there's a hack. Basically, if you're going to do an inversion, you basically just put one in the numerator and put whatever it was in the denominator. And it seems to work out to at least all the digits that I had checked. But what are we talking about today? Today, again, we go to our friend Wikipedia, and again, links are all the doobly-doo below for anyone that wants to go check it out, or maybe do some exploration of the computational universe that may or may not actually have equivalence to our realm of persistence. Total conjecture there, I'm just saying. The conductance quantum, just to reiterate, the conductance quantum, denoted by the symbol G0, is the quantized unit of electrical conductance. It is defined by the elementary charge E and the Planck constant H as G0 equals 2E squared over H. That comes up to that number there, which happens to be big S. It was a little less. Typically, we use that to represent seconds. That's big S. That's for the Siemens. Just the next part. It appears when measuring the conductance of a quantum point constant, and then more generally, is a key component of the Landau formula, which relates the electrical conductance of a quantum conductor to its quantum properties. It's twice the reciprocal of the von Klitzing constant. Groovy. Okay. So we were just talking before again. The conductance quantum, well, let's go over here. G0, I literally just noticed this. It's an S. It's Siemens. The inverse conductance quantum, or inverse of conductance quantum, yes. It's got that crazy omega thingy right there. That's Ohms. We go to our friend Wolfram Alpha. An Ohm. Okay? We got that. It's equal to all those things. So it was also at once expressed in 1 times 10 to the 9 emus. Personally, I think that's an undervalued unit. Just my personal opinion. But what are its dimensions? This is going to be interesting. Okay, as I derive, it's amperes to the negative 2 kilogram meters squared, seconds to the negative 3. What the heck does that mean? At least as far as our ingredients of reality, to the best of our knowledge and experimental measurements, its basic unit dimensions are mass length squared times to the negative 3, current to the negative 2. So basically you do 1 over that. Yeah, you get your Siemens. Dun, dun, dun. Okay, I'm sorry, I got the some ultimate battle in my head. So okay, how are we going to solve it? We're going to solve it with this equation right here. Okay, what is this equation? This is G0 to the negative 1. Okay. So basically we just flip the symbols and stuff. That's kind of what we had going on over there. But hey, welcome, Jax. Good to see you, my friend. Hey, Whitechapel, thank you for joining, my friend. Yeah, we're just going over like the inverse. Basically, okay, to skip ahead, you could literally just do what we did yesterday and just throw put 1 at the top, throw some brackets, and then just divide it all. It's like, okay, that's cool. We get this number here, which skip ahead, sorry. It's basically that. So I didn't look more than like 3 or 4 significant digits past like whatever we're looking for because they have a cutoff at 10 here. Okay. We go back here, but those of you that have been following this for a while, hey Rick, good to see you. Oh, Fractal, hey, thank you for joining. Hey, Fractal, you say that. You say that. Give give that a little bit more time to release things, because I'm not gonna say you're wrong. Can neither confirm nor deny. I don't know. It's fascinating place in which we live. Okay. So what are we doing here? In order to do that, basically we take our friend pi, because well, who doesn't like pi? We divide it by Joe1 squared. What the heck is a Joe1 squared? We go over, oh my god, did oh, I had him the other, oh, hold on. Let's try to be brave here. Okay. Yeah. When it's in your base Google tab, you may have gone to it a few times. Okay. This is our hyperbolic vortex equation. Basically, the claim is here. We take this standard geometric formula here. 1 over x plus x cubed divided by 2 pi, which is a circle. And we set that equal to I raised to the I. Then we raise that to the negative pi divided by 2. And we have our lambda here, which happens to be the magnitude of the Planck mass gap, which is interesting. It gives us this answer here. It has 4 answers. We take the first answer, and we square it. So we do caret up on Wolfram alpha. Okay. Gives us this number here. What the heck is 0.0072975, yada yada. Well, the interesting thing is, Professor Feynman basically to summarize, he's like, we got this dang number popping up everywhere. The claim is that is the fine structure constant derived geometrically. So we got 0.00729735256. So that's what's listed on Wolfram alpha. There are experiments. I think there was one at Harvard. They're get updating and changing the lasers apparently. They're claiming this is like a 6 or something like that. So we want to be open and transparent as much as we can because we're looking for truth. We're not just trying to be like, oh, look at us, because, well, it's a fascinating question. And I think it might help us move along. That's at least my claim. Okay. So we take that Joe1 squared, which the claim is that's the fine structure constant. Oh god, we're skipping ahead. Okay. So we've got, hold on, I need to restart my anime music. I've been doing this for a little while. Yes, I am a weeb. These things happen. Wrong thing. All right. So we got our pi divided by the fine structure constant, aka Joe1 squared. So basically we just flip that from yesterday, and we do the same thing with our boundary conditions over here. Like Planck time was on top, Planck charge squared was on top. In this case, we flipped it, so we have our primary action, which is pi divided by Joe1 squared. Cool. We have our boundary conditions, our ingredients for our recipe for reality. This is going to be the claim. So we got the Planck length squared times the Planck mass. And that's all over the Planck time times the Planck charge squared. Now, for those of you who've been paying attention, those are not the units we initially showed for the ohms. The units we showed for the ohms, I think I was right there. All right, is mass and length. So on the top there, we have mass and we have length. Time to the -3 and current to the -2. We have, God, all over the place. All right. We've got time. We've got charge squared. Now, the very interesting thing that one notices, and certain folks have been talking about this for a little while. I know there's at least 2 of them. Not saying I've had to. Just wait. It's all right. Fun stuff will be coming. But if we take the Planck mass multiplied by the Planck length. And then we divide it by the Planck charge squared. So basically, we'll divide by that. Wolfram alpha will set it up for us. Oh god, that's right. I need to do multiplication because it thinks I'm talking about a list. Because obviously, apparently most people when they're talking about Planck units don't plug it into Wolfram alpha that way. Maybe I should set a bug error. Okay. Oh god, what the heck? Oh, I didn't do negative. There we go. See, new error. Okay, multiplication, and we go to our friend here. Okay, comes to be out to be 1 times 10 to the negative 7 precisely kilogram meters second squared amperes. Oh god! But the whole point of this is interpretation is magnetic permeability. Wait a second, we only mass, length, charge. What? We didn't put any time in there, did we? Mass, length, time to the negative 2, and then current to the negative 2. Oh, very interesting. Oh, wait. Oh, we're actually missing a dimension of time, aren't we? Should. Oh, wait. Yeah. Because why are we missing the time? Because that was the wrong equation. See, look, we already have the unit of time there, so it should add up there. See, you need to question yourself because if you don't, other people will. It's hard though. I remember I noticed the magneton difference. I'm like, should I even tell Pat about this? Oh, I want this to be correct. It's like, no, you tell people this, and things got a lot more beautiful. But it's hey, Jax. Hey, I try to help people out where they can. I think I may or I can either confirm or deny if I've done enough for everybody. Commonwealth. Okay. So we have our primary action. We have our boundary condition. Okay. We got things. Okay. Excuse me. We got stuff. We got our dimensional ingredients. There's a playlist if you want to play around. All right. So we got stuff and it's doing a thing. It's actually doing 2 things. We get pi divided by the fine structure constant, and we have our terminal action. Basically, right around that 10 to the negative 7, usually around 7 decimal place in a lot of these things start to get a wee bit wonky. So basically, we have this, which utilizing this is the universal binomial factorization equation. So we got primary action boundary, so stuff doing things. Excuse me. Yes. We got some stuff. No, excuse me. We got some stuff doing a thing. Okay. We multiply that by our terminal action. So we got it doing another thing on a different scale. So that's 1 plus, in this case, because it was minus the other day, because it's the inversion. We got 1 plus the square root of zeta 3. It seems to be related to the Riemann zeta function. It's a very fascinating thing. We'll get into that at some point in the future. Mostly because I'd like to figure out what's going on. And we multiply that by j theta squared. What the heck says j theta? Go back. Uh, 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 There we go. It should be enough. All right. J theta, again, hyperbolic vortex equation here. I forgot to link it this time. I apologize. It should be in the other videos. But if we swap over from Cartesian form to trigonometric form, which I still don't even, okay, I kind of have an idea. I never really got trig down. And now it's like, oh, I'm just seeing, oh, it's like reflections and symmetries and stuff. How very cool. Basically, we just take this number here. We take the magnitude of that. That's our thingy that we plugged in there. And this is basically that Planck mass, Planck length, Planck charge. So it comes up to be 10 to the negative 7. So when we throw that all in, this is what we get here. So again, we've got our pi over our J1 squared there. All right, pi J1 squared. And then we get our boundary conditions on this next level. Let's make it a little easier to see. Okay. So in this, Planck length squared times Planck mass, that's the magnitude, and that's Planck time. We're dividing by it, so if we plug it in shorthand, we do -1, so we don't need to use many brackets. And then this is the Planck charge squared. So that's just that right there. We just literally just threw the numbers in. And our terminal action is 1 plus the square root of zeta of 3 times j theta, which was that trigonometric form we had there. It's times 10 to the -7. So in this case, Wolfram alpha pleasantly just divides it by 10 to the 7. So the inverse conductance of quantum that we're looking for, and the claim is this is exact. It's going to be 12,906.40372. Okay? So according to our derivation, the number we get is 12, 12, 906, 906, dot 403, dot 403, 73, 72. We are off. Yes, yes. That very last significant digit. It appears that we are off. So we're just being open and transparent about that. So let's see, because they're cutting this off and saying it's exact. 7. Oh, the next digit is a 0. Now again, to our best levels of our measurements and our derivation, because also this happens to be directly related, or at least according to Wikipedia, as 2 elementary charges squared divided by Planck's constant h. Which again, I think we cut off at about 10 significant digits right there when we updated SI there. Okay. So the claim is that this should be a 3 and the next digit is a 0. Because depending on our measurements, depending on our derivations, it basically, at least according to Thad, when they redid the SI back in 2019, and apparently they were still rolling it out through 2022, there was about a 3.5 sigma swing. So it's like, okay, maybe there's a tiny bit of, maybe a little bit of wiggle room. And at least that's the claim. And again, we're not going to hide it or anything like that. That would be dishonest. And we're trying to science. And science is seeking the truth, right? Otherwise, why would we be doing it? Hey, welcome, awesome one. Good to see you. Yes, squirrel squared. I will not comment on whether that is true or false. I cannot. I personally am biased. But okay. And again, these different forms are very fascinating. But I'll make it. And again, if you do 1 over that, you literally get the same thing. So I'll make the claim that, my friends, this appears to be a geometric derivation of the inverse conductance of quantum. At least that's going to be the claim. And again, last digit is off. I must stress that, but at least according to us, the following digit is a 0. If that was a 9, maybe a little less confidence. It's a 0. Next digit is a 6. It is a 6, 0.1. But hey, when you're measuring very precise things, we try to do the best we can. And that was why we updated. I think most of these things are based upon the speed of light, which we have to 9 measured significant digits to the best of our guesstimation, because measuring light is funky in and of itself. But yeah, that's all we got for right now. So thank you all for watching on this bustling Friday night. Happens to be a wee bit steamy out here, and the the great Commonwealth of Massachusetts. But take care of yourselves, everyone. I think there's some really cool stuff coming. At least that's what I'm going to claim. So take care of yourselves. Peace out.